never going to stop exploring the unknown in air and space. We're not going to stop innovating for the benefit of humanity.
There were many unknowns about the universe when scientists planned and designed the Hubble Space Telescope, the most groundbreaking astronomical observatory of its time. One of these unknowns was the existence of stars and galaxies a few 100 million years after the Big Bang. Even if they were aware of these early stars and galaxies, they lacked the technology to make Hubble see them. Science had moved on by the time they built it, and science had changed in some ways. And in the 1980s, shortly before Hubble's 1990 launch, astronomers discovered that galaxies formed much earlier than expected. It became clear that another, even larger space observatory would be required to reach those early stars and galaxies, which had lit up the universe after hundreds of millions of years of darkness following the Big Bang, when the expanding space was only filled with hydrogen atoms. The technology that would eventually allow this observatory, now known as the James Webb Space Telescope, originally known as the Next Generation Space Telescope, to see the mythical first light in the universe had not yet been developed. Infrared detectors that could collect the faint light emitted by those early stars and galaxies more than 13 billion light-years away were the missing piece of the technology. The Hubble Space Telescope was designed to detect visible and ultraviolet light. These early galaxies do emit visible light, but due to their distance, the wavelength of this light is stretched into the infrared region of the electromagnetic spectrum by a process known as redshift. McCaughrean was one of the scientists at the University of Edinburgh in Scotland who developed early infrared detectors, a technology that has now culminated in 4 cutting-edge scientific instruments of the James Webb Space Telescope. In the early 1980s, infrared pictures were taken with one detector scanning the sky 1 pixel at a time, said McCaughrean. It took forever. My PhD thesis was all about the first camera which could take 2D infrared images. We had 58 times 62 pixels, and that was 4,000 times more than everybody else had because they only had one. McCaughrean later moved to the United States to work on the near-infrared camera and multi-object spectrometer, NICMOS, the Hubble Space Telescope's first infrared detector, installed during its second servicing mission in 1997. NICMOS, which consisted of 3 infrared detectors with 256 by 256 pixels each, provided Hubble with the first glimpse of the infrared universe. Since Hubble's early days, technology has advanced significantly, and the James Webb Space Telescope project has pushed it even further. The detectors on JWST have 2000 by 2000 pixels, and it has lots of them. So what do all these pixels allow the James Webb Space Telescope to do? The giant mirror of the James Webb Space Telescope directs light from stars and galaxies to 4 cutting-edge instruments designed not only to take images, but also to analyze the chemical composition of the nearby and distant universes. This is accomplished through the use of spectroscopy, a technique that examines how matter in the universe absorbs light. Because different chemical elements absorb light at different wavelengths, astronomers will be able to reconstruct the composition of stars, nebulae, galaxies, and planets visible through James Webb Space Telescope. The universe contains many mysteries that scientists are attempting to solve, one of the most perplexing being the origin of the universe itself. While there are many hypotheses, they must all be proven, and the proof is focusing on one thing: determining what happened at the beginning of the universe. That is no small feat, as it necessitates the most advanced technology ever devised. To study some of the oldest objects of formation in existence, the tool must be able to see the edge of the universe. Some of these objects have been around for billions of years, and it's time to debunk them, which is where the JWST comes in. The JWST is simply the most powerful telescope ever thought up by humans. Galileo Galilei, the father of the telescope, must be pleased with how far we have progressed with his invention. However, that progress comes at a high cost of $10 billion, as well as numerous panicky moments during the launch. Since the launch and installation of the JWST in its permanent orbit went smoothly, NASA can now sit back and enjoy the massive scientific returns that the massive Space Observatory and the JWST have been delivering. The JWST has revealed truly shocking things about our universe in the short time scientists have been working on it, many of which the scientists did not see coming. At this rate, it is not an exaggeration to say that the JWST will put everything we thought we knew about the universe to test. As expected, the JWST is already taking us back in time and closer to the edge of the universe. Scientists refer to this period as a glimpse of the early universe because of its ability to detect the faint light of extremely distant galaxies that glow in infrared light, which is invisible to the human eyes. As a result, the image in question has aided astronomers in better understanding how galaxies formed and evolved in the early days of the universe. Scientists have been intrigued by the image of a galaxy cluster MACS 0647, as well as the distant galaxy MACS 0647 JD. The cluster appears as a dazzling collection of galaxies that glow like precious gems against the dark background of space. The distant galaxy is visible due to an observational phenomenon caused by the cluster. This is known as gravitational lensing, and it happens when galaxies in the foreground act like magnifying glasses, allowing us to see more distant objects behind them. The galaxy MACS 0647 JD was pinpointed using small boxes, and more detailed images of the galaxy are aligned among the right side of the image. The cluster essentially magnifies the galaxy, causing it to appear in 3 different places within the image. Each box on the right highlights different aspects of the galaxy. While MACS 0647 JD was discovered using the Hubble Space Telescope 10 years ago, it didn't take long for the JWST to reveal something surprising about the cluster. There are 2 features, and here's what happened. Using Hubble, it was just a pale red dot, and we could tell it was really small, just a tiny galaxy in the first 400 million years of the universe. But scientists were able to resolve 2 objects using the powerful JWST. However, the question of whether these 2 galaxies or 2 clumps of stars within a galaxy remains unanswered. They just don't know yet. But guess what they're counting on to find out? The JWST. These are not even the most distant objects discovered by the JWST. That distinction belongs to one of the earliest galaxies formed not long after the Big Bang. This particular galaxy was captured approximately 350 million years after the Big Bang, or the beginning of the universe. Not long after the powerful space observatory began its infrared observations of the cosmos, the Glass Z12 galaxy and another galaxy formed about 450 million years after the Big Bang were discovered. Prior to this, the Hubble Space Telescope discovered GNZ11, which existed 400 million years after the Big Bang and was discovered by the Hubble Space Telescope in 2016. Indeed, the scientists using the JWST stated that as soon as they began collecting data, they realized that there were many more distant galaxies than they expected, implying that the universe produced galaxies faster and earlier than the researchers thought. Many galaxies had already formed a few hundred million years after the Big Bang. The JWST has just opened up a new frontier, providing us with a front row seat to better understand how it all began. Both galaxies have sphere or disc-like shapes, but their sizes are a tiny fraction of the size of the Milky Way galaxy. The 2 galaxies are extremely distant from us, but they are extremely bright and rapidly generate stars. Further research indicates that galaxies may have begun to appear in the universe just 100 million years after the Big Bang took place 13.8 billion years ago. This timeline calls into question astronomers' theories about how and when the first galaxies formed. The early universe was undeniably chaotic and dense, but the structure of the 2 galaxies turned out to be calm and orderly. Do you know what else has perplexed these scientists? It is the overwhelming brightness of these 2 galaxies. One theory is that the galaxies were enormous and had a large number of low-mass stars, similar to the type of galaxies that formed later in the universe's history. Another possibility is actually the opposite, smaller galaxies with fewer yet highly brilliant stars. These brilliant objects, known as population 3 stars by scientists, have long been thought to be the earliest stars to be born in the universe. The first stars in the cosmos are thought to have been extremely hot and made of hydrogen and helium. The heavier elements generated when the earliest stars exploded must have been present in the stars that followed. No population 3 stars have ever been discovered in our local universe. Scientists, on the other hand, are depending on large telescopes like the JWST, which can peek back into the distant universe, effectively looking back in time to glimpse the first population 3 stars one day. It would not be surprising if the older of the two galaxies, Glass Z12, contains population 3 stars. The JWST continues to shatter records by previous telescopes, and what's more, it's doing it in the short time that it's been fully operational. While the two previously stated faraway objects may have sufficiently wowed you, there is another candidate for the galaxy, CEERS 93316. This object, formed about 250 million years after the Big Bang, has set a record redshift of Z equals 16.7, displaying the strength of the juggernaut designed and launched by NASA. CEERS is an abbreviation for Cosmic Evolution Early Release Science Survey, and it is a specific program designed for imaging with the JWST. Follow-up spectroscopy observations will be used to confirm the redshift. That's why it's still referred to as a galaxy candidate. The investigation has previously established that CEERS 93316 cannot be a low-mass star or an unobstructed active galactic nucleus. This is based on imaging data from the primary imager of the NIRCam JWST. Following the Big Bang, the universe entered what is known as the Dark Ages, which is the period before any of the stars visible today were born. The observations of this galaxy, however, push observations back to the time when astronomers assumed the earliest galaxies ever formed. According to NASA, the JWST can detect galaxies with redshifts larger than 20, corresponding to less than 200 million years after the Big Bang. However, these galaxies will most likely be incredibly difficult to find. Nevertheless, the discovery of CEERS 93316 gives scientists optimism that they exist. If the terms redshift and shifted light have left you bewildered, here is what they mean. The universe after the Big Bang was like a boiling soup of particles, such as protons, neutrons, and electrons. However, as the cosmos cooled, protons and neutrons began to combine to form ionized atoms of hydrogen and helium. The atoms of hydrogen and helium attracted electrons in this ionized state, transforming them into neutral atoms, allowing light to flow freely for the first time in the cosmos because it was no longer scattering off free electrons. This was a watershed moment in the universe because it was no longer opaque. However, it would take some time, perhaps a few 100 million years after the Great Bang, for the first sources of light to develop, bringing the cosmic dark ages to an end. This is highly intriguing since it implies that the universe was ready to transmit light before light sources were born. So how did the stars that fused the existing hydrogen atoms into additional helium look like as the universe's first light? We don't know that yet, and we also don't know when the first stars formed. These are the questions that scientists are hoping the JWST will address. What about light that has been shifted? Imagine the light that left the earliest stars and galaxies about 13.6 billion years ago and traveled across space and time to reach our telescopes. This means that we are viewing these objects as they were 13.6 billion years ago when the light originally left them. However, by the time this light reaches us, its color or wavelength will have shifted towards red, a phenomenon known as redshift. Because the universe expands, the distance between objects stretches, forcing objects to move away from one another, according to Einstein's general relativity in this example of very distant objects. Furthermore, any light in their space will expand, and the wavelength of the light will shift to longer wavelengths. This can make distant objects appear very faint or invisible at visible wavelengths of light, since that light reaches us as infrared light. When scientists mention redshift, they mean that light emitted by the earliest stars and galaxies are visible, or ultraviolet light is shifted to redder wavelengths by the time we observe it from Earth. For very high redshifts, which are the objects that are the furthest away from us, visible light is generally moved into the near and mid-infrared regions of the electromagnetic spectrum. As a result, in order to see the earliest stars and galaxies, we need a strong near-mid-infrared telescope, which is exactly what Webb is. Able 2744Y1 is one of the galaxies discovered by scientists near the farthest edge of the universe. This galaxy is unique for several reasons. For starters, Able 2744Y1 is so far away that the light from it arrives after 13 billion years of travel. Keep in mind that the universe is considered to be 13.8 billion years old. One interesting aspect of Able 2744Y1 is that we are viewing it as it was only 650 million years ago. Because the light from distant things in space has taken so long to reach us here on Earth, this is true of all distant objects in space. Spitzer, Chandra, and Hubble telescopes were used to discover Able 2744Y1. But how could three telescopes work together to find a single item? The Hubble Space Telescope gathers photos in visible and near-infrared light, while Spitzer uses the infrared region of the electromagnetic spectrum. Scientists use Chandra to collect additional data utilizing X-ray wavelengths. Astronomers were able to observe galaxies up to 100 times more distant than any of the observatories could have done independently by merging data from these three space telescopes. The astronomers from the Instituto de Astrofísica de Canarias, IAC, and Laguna University in Spain began with the Hubble Space Telescope, which detects the galaxy in question. This is followed by Spitzer, whose instruments are used to compute the distance between the object and its location. The telescope also aids in determining the number of stars in the galaxy. When photographing Able 2744Y1, the scientists also employed gravitational lensing. Because images from faraway galaxies are brought into focus by galaxies closer to Earth, the underlying principle is similar to how a magnifying glass bends sunlight. Albert Einstein anticipated this natural telescope to view the farthest distant objects in the cosmos in his general theory of relativity. How big is this galaxy? Astronomers estimate that Able 2744Y1 is about 50 times smaller than our own Milky Way galaxy, or about 2,300 light-years in width. What this galaxy lacks in size, it makes up for in star formation pace. It produces stars at a rate 10 times that of the Milky Way, but this is typical of galaxies in the early cosmos. The redshift of the Able 2744Y1 galaxy is 8. Before the finding of Able 2744Y1, the furthest confirmed galaxy had a redshift of more than 7. So far, the JWST has shattered all of these records. However, only last week, astronomers using the James Webb Space Telescope discovered 3 small galaxies that may have contributed to one of the largest cosmic remodels in history. The findings, presented at the American Astronomical Society (AAS) meeting in Seattle, Washington, and published last week, could explain reionization, the period when harsh radiation tore apart a fog of hydrogen atoms hanging over the universe, allowing stars and galaxies to be seen for the first time. Researchers opted to conduct further spectroscopic investigations of 3 galaxies in the SMACS 0723 image that appeared to be very distant. However, when James Rhodes, an astronomer at NASA's Goddard Space Flight Center in Greenbelt, Maryland, and his colleagues first examined the spectra of the trio, they concluded that the galaxies appeared like neighboring objects. They bore an amazing resemblance to green pea galaxies, which were discovered in 2009 by a citizen science project called Galaxy Zoo. Green pea galaxies were named by their bright color and compact size. They are only 5% the size and 1% the mass of the Milky Way. But don't be fooled by their diminutive size. They produce stars at an incredible rate, nearly 100 times faster than astronomers would predict given their mass. They also appear to have a low concentration of heavy elements. Their greenish color is caused by the glow of ionized oxygen, a relatively light element heated by newborn stars. Green peas have captivated astronomers because, despite being observed only in the nearby universe, their properties are similar to those expected of early galaxies. Because heavy elements take time to form, the first galaxies, for example, are thought to contain only light elements. An astronomer at Goddard Space Flight Center, Sangeeta Malhotra, joked at the AAS meeting on January 12 that they are Peter Pan galaxies because they haven't matured. This is why Rhodes, Malhotra, and their colleagues were enthralled by the spectra of the 3 galaxies studied by the JWST. The galaxies are from the early universe but look like nearby green peas. The trio, like green peas, are small and have strong emission spectra, which means they produce stars quickly. They are also low in elements heavier than hydrogen and helium. In fact, the most distant of the 3 contains about 2% of the oxygen found in the Milky Way. That is possibly the lowest amount of oxygen ever observed in a galaxy. Another source of excitement can be traced back to 2016, when astronomers, including Thuan, reported a green pea ejecting a swarm of ionizing photons into the intergalactic medium 3. The vast majority of galaxies observed in the nearby universe do not do this. With so many stars in such a small volume, green peas may be able to punch channels through the interstellar medium, allowing energetic radiation to escape. That could imply that early universe objects, such as the trio, provided the energy required to free the cosmos from its dark age. According to scientists, the universe has a radius of 46.1 billion light-years, which is the limit of the observable universe. But there is much more out there. How do we know what exists beyond the observable universe? We can draw conclusions based on known physical rules and the things we can measure in our observable universe. For example, we understand that the universe is spatially flat on the cosmological scales. It is neither positively nor negatively curved to a precision of 0.25%. If our existing physical laws are right, we can establish boundaries on how big the universe has to be before it turns back on itself. The observations from the Sloan Digital Sky Survey and the Planck satellite provide the best data for our extrapolation. According to the two sources, if the universe does curve back in on itself and the close part that we can see, it must be at least 250 times the radius of the observable region. This implies that the unobservable universe, assuming no topological oddities, must be at least 23 trillion light-years in diameter, with a volume of space more than 15 million times larger than the volume we can observe. However, there are convincing arguments that the unobservable universe is much larger than that. How? The hot Big Bang may signal the beginning of the observable universe as we know it, but it does not mark the birth of space and time. This is due to the fact that prior to the Big Bang, the universe experienced a period of cosmic inflation. Rather than being filled with matter radiation and being hot, the universe was filled with the energy inherent in space itself, expanding at a constant exponential rate and creating new space at such a rapid rate that the smallest physical length scale, the Planck length, would be stretched to the size of the currently observable universe every 10 raised to the power of -32 seconds. Sure, inflation ended in our part of the universe, but how long did it last before it ended and the resultant hot Big Bang? It's possible that the universe where inflation happened was barely bigger than what we can observe. Perhaps in a year's time, evidence for an edge to where inflation happened will emerge, and we will have to revise our understanding of the cosmos once more. Let's hear what you think is at the edge of the universe in the comments section below.